Hello, students. In this lesson, we will discuss the hazards of salt and water content in crude oil. Crude oil extracted from underground always contains water. This water contains dissolved salts such as sodium chloride, calcium chloride, and magnesium chloride. Although it undergoes desalination and dehydration treatment at the oil field, the crude oil delivered to the refinery still contains a certain amount of salt and water. With the deepening of crude oil extraction and efforts to enhance oil recovery, the properties of crude oil are becoming increasingly poorer. Some crude oils have salt contents as high as 300 to 400 mg per liter and contain small amounts of sediment, emulsified water, etc., posing certain difficulties for subsequent production. This lesson will cover three main points. First, the forms of salt and water in crude oil. Crude oil extracted from formations contains varying amounts of mechanical impurities, C1, C2 light hydrocarbon gases, water, and inorganic salts like sodium chloride, magnesium chloride, and calcium chloride. Crude oil entering the refinery still contains varying amounts of salt and water. Salts are mostly dissolved in the water, with a small portion suspended as crystals in the crude oil. Water is mostly dispersed as fine droplets in the oil, forming a relatively stable water and oil emulsion. Water containing crude oil is a relatively stable water and oil emulsion, as shown in the diagram on the right. The difficulty in dehydrating it is mainly due to its highly dispersed emulsified state. Water and oil emulsion is formed by mixing oil, water, and an emulsifier. In this system, water is dispersed as small droplets in the oil. The water phase is the internal or dispersed phase, and the oil is the external or continuous phase. The addition of emulsifiers can reduce the interfacial tension between oil and water, thereby reducing the energy consumption during emulsification and facilitating both the emulsification process and the stability of the emulsion. However, the more important role of reducing interfacial tension is that surfactants form a directed monolayer at the oil-water interface. That is, the hydrophilic groups of the surfactant face inward, and the lipophilic groups face outward, tightly surrounding the water droplets. The counterpart to water and oil emulsion is oil and water emulsion. Milk is a typical oil and water emulsion. Oil and water system is one of the common emulsified systems, denoted as OW. It is an emulsified system where oil is dispersed in water. Oil is the internal phase, and water is the continuous external phase. Second, the hazards of salt and water in crude oil. The hazards are divided into four aspects: increased energy consumption, process disruption, equipment corrosion, and impact on product quality. First, look at energy consumption. Feedstock undergoes phase changes of vaporization and condensation during distillation. Water has a very high latent rate of vaporization. If water undergoes phase change together with the crude oil, it inevitably consumes a large amount of fuel and cooling water. Furthermore, when crude oil passes through heat exchangers and furnaces, the water it contains evaporates as the temperature rises, and salts dissolved in the water will precipitate out, forming salt scale on the pipe walls. This not only reduces heat transfer efficiency, but also decreases the flow area inside the pipes, increasing flow resistance. After water vaporizes, its volume increases significantly, causing the system pressure to rise, leading to increased pump outlet pressure and higher power consumption. For example, in a 2.5 million ton per year atmospheric and vacuum distillation unit, if the crude oil water content increases by 1%, the heat energy consumption will increase by 7 GJ per hour. Second, it disrupts the stable operation of the distillation column. Water has a much lower molecular weight than oil. After vaporization, it increases the vapor load inside the column. Fluctuations in water content inevitably disrupt the normal operation of the column. In minor cases, it affects product separation quality. In severe cases, It can cause column flooding accidents due to water's bumping. Third, it corrodes equipment. Chlorides, especially calcium chloride and magnesium chloride, can hydrolyze when heated in the presence of water, releasing hydrogen chloride, HCl. The latter, in the presence of liquid water, forms hydrochloric acid, causing corrosion in the low-temperature sections at the top of the distillation column. Magnesium chloride and calcium chloride generally begin to hydrolyze at 200 degrees Celsius. When their concentration is high, hydrolysis can start at 120 degrees Celsius. Hydrolysis can occur in an aqueous solution or proceed using their own water of crystallization. When the temperature reaches 300 degrees Celsius, sodium chloride will also undergo hydrolysis. When processing sulfur-containing crude oil, sulfur compounds decompose releasing hydrogen sulfide, H2S, which reacts with metals to form iron sulfide, FeS. This can deposit on the metal surface and act as a protective layer. When hydrogen chloride is also present, it reacts with the iron sulfide, destroying the protective layer and releasing hydrogen sulfide, further aggravating corrosion. Fourth, it affects the quality of secondary processing feedstocks. The salts contained in the crude oil become concentrated in the vacuum residue after distillation. When the residue undergoes secondary processing, whether catalytic cracking or hydrodesulfurization, the sodium ion content in the feedstock must be controlled, otherwise, it will poison the catalyst. When high salt residue is used as feedstock for delayed coking, salt scale in the furnace tubes can lead to coking. The produced petroleum coke will also be of lower grade due to high ash content. During the electric desalting process, a significant amount of filterable solid material also deposits at the bottom of the desalter vessel. Using a backwashing method can remove these solids along with the water. This reduces fouling in the unit's furnace tubes and heat exchangers, improves heat transfer efficiency, and extends the operation cycle. To reduce the hazards of salt and water in crude oil processing, deep electric desalting is now required for refineries equipped with heavy oil catalytic cracking units. Next, the third point, the targets for desalting and dehydration. Currently, the general requirement for crude oil desalting and dehydration in refineries worldwide is typically a salt content of less than 5 milligrams per liter and a water content of 0.1% to 0.2%. After atmospheric and vacuum distillation, the salt in crude oil is primarily concentrated in the residue. Heavy oil catalytic cracking, developed in recent years, is a processing route with high economic benefits. However, sodium damages the lattice of zeolite catalyst. Therefore, catalytic cracking has stricter requirements for feedstock, demanding a sodium chloride content of less than 3 milligrams per liter after crude oil desalting. Students, in your future work, you must always adhere to the principle of quality first and the requirement for continuous improvement. Strictly control the indicators and ensure the quality of both feedstocks and products. All right, that concludes this lesson. Goodbye, see you in the next class.